Hello everyone. In this module we will learn about X-ray diffraction, which is used quite commonly to understand the construction materials. So the goal of this lecture will be to just know about the X-rays, right, and how can we use these X-rays to understand the material, right. So we will start with the background. That is very important to know the history. So X-rays were discovered by German physicist Röntgen in 1895, and he received the first Nobel Prize of Physics for this. Okay. So what was the difference? Unlike ordinary light, X-rays are invisible, you can't see them. Okay. And X-rays have more penetrating energy than light and could easily pass through the human body, wood, quite thick pieces of metal and other opaque objects. These were the observations, right. So X-rays were immediately put to use for detecting, for an example, a broken bone, right, or the position of a crack in a metal casting, which you will see in the next slide. So here you see these radiographs, right. You can identify the bone fracture, right. So and also similarly in the casting, if there is a crack, you can see it, right. So that was the significance of this discovery, that without even knowing much about X-rays. Why X-rays? Because they did not exactly know the nature of these rays, so they said X-rays, but they could use these X-rays to for an example identify the bone fracture or cracks, right, in like when you do casting of metals. So that was huge benefit of these X-rays, right. So they were put to use immediately, right, for these applications. So basically X-rays are electromagnetic radiation of same nature as light, but of very much shorter wavelength, right. If you will come to this, if you look at the electromagnetic spectrum, what you find is the wavelength of X-rays is much shorter than the wavelength of light. And the unit of measurement in the X-ray region is in the angstrom, right. 1 angstrom is 10 to the power minus 10 meter. Okay. X-rays used in diffraction have wavelengths lying in the range of 0.5 to 2.5 angstrom, right, whereas the wavelength of visible light is of order of 6000 angstrom. See the difference. So the X-rays which we use for diffraction are much shorter wavelength, right. So here is again the electromagnetic spectrum, right? Everyone is familiar with this. Here is the visible light, what we can see in terms of wavelength. So you see wavelength in angstrom, right. Visible light is around 5000 angstrom, right, roughly around that range, 5000, 6000 angstrom, and X-rays are somewhere here in this range, right. It can range from 0.01 to 100 angstrom, right. So this is the, in this direction wavelength is increasing. Wavelength is increasing, the frequency will decrease, right. So in this direction frequency is increasing. All of you know the relation between wavelength and frequency. Okay. So you can see where it is, right. So it has shorter wavelength than visible light, right, and this is the range 0.01 to 100 angstrom. And also you can see energy. So frequency is nu, right, and we know that energy can be expressed in terms of h nu. So you say in this order energy increases in this direction. Okay. Okay. So, we know X-rays are invisible, have shorter wavelength, that means higher energy, h nu or hc over lambda, right. This we will keep using this relationship, also you should remember this, right. Shorter wavelength means higher energy. Okay. So, now the question comes, how do we produce these X-rays, right? If they are so advantageous, it is good to know how they are produced. So, X-rays are produced when an electrically charged particle of sufficient kinetic energy rapidly decelerates. That charged particle could be electron. Okay. So, in this case you see X-ray tube. What does X-ray tube will contains? A source of electron, we are talking about electrons, and also two metal electrodes, because two metal electrodes should be connected, or there should be very high potential, right, which can accelerate these electrons, right. We are talking about volt 30K to 50K voltage difference, right, very high voltage across these metal electrodes, cathode and anode. And X-rays are produced when the electrons strike the target, which is anode, right, at very high velocity. So, you are generating electrons, right, and there is a voltage, very high voltage. So, electrons are going to hit the target, and then X-rays are produced when these electrons are when they strike the target. So, what happens? Most of the kinetic energy, because these electrons have very high kinetic energy, right, is converted into heat. Most of it is converted into heat, right, less than 1% being transformed into X-rays. So, we are looking at these, right. So, that is how you generate X-rays, is the schematic of an X-ray tube, right. You see tungsten filament here in this case, where which you will use to generate electrons, right, connected through transformer, and there is a high voltage across anode and cathode. You see the target metal, it hits the target metal and X-rays are emitted, and you can get it. These are the directions in this case, right. Also, because the target will get really hot, you need a mechanism to cool it down. So, you see a cooling water that is used to cool the target. Okay. This is the typical schematic of X-ray tube. Okay. So far we know what we know. Okay. You have electrons of very high energy striking a target, right, will give rise to X-rays. But we want to know, we want to probe further, like, so what happens, right. So, when now we analyze this X-ray which is coming out, right, now we are saying, okay, we are analyzing the X-rays which are coming out, they contain various wavelengths and associated intensity. So, you can plot, suppose you analyze the X-ray coming out of the metal target, it will have, for an example in this case, let us see, suppose we are operating at 10 kilovolt, so 10 kV, okay, that is the voltage difference, right, 10 kV. So, you will get these, this is the, what does it say? It is a mixture of wavelengths and also X-ray intensity changes, right. First of all, you do not see any X-ray, there is a shorter wavelength beyond, I mean there is no X-rays, right, in this range. Then it starts here, then you have these different wavelengths, right, of different intensity. Also another way of looking at it is like wavelength, this is wavelength is increasing, right, that means energy is decreasing, right. Again always remember this relationship, right. If the wavelength is decreasing, that means energy is increasing, wavelength is increasing, energy is decreasing. Okay. So, this is called continuous spectrum, that is what is in that X-ray typically, right. So, again now you increase this 10 kilovolt to 15 kilovolt. Okay, what happens? The curve shifts towards left, right, and then you see again mixture of wavelengths having different intensities. Clear? The curve is similar, the only thing is it has shifted towards left because we have more energy, right. See, you are supplying more energy, then that means your lambda will be smaller. So, lambda in this case, shorter lambda will be smaller than this. Does it make sense? You can again refer to this relationship E is equal to Hc over lambda. So, if you have more energy, that means lambda is shorter. So, as you are increasing this voltage, that means you are accelerating the electrons, right. So, to 20 kV, again you see shift towards left, again you see similar spectrum, it is called continuous spectrum, it is continuous or white radiation, right. But see, there is something happens. So, when the voltage on an X-ray tube is raised above a certain value, in this case if you see like 25 kV, okay, what is happening? Then the characteristic of the target metal, a sharp intensity maxima appears, which is not present in other continuous spectra, right. Only when you have, suppose in this case you see for the case of 25 kV, you see appearance of these sharp maxima. Okay, so the associated wavelengths, they occur at, the associated wavelengths are called characteristic lines, and it is very specific to metal, particular metal. It is a characteristic of the target metal. If you change the metal, for an example, this wavelength will change. But what is interesting is, like, if you increase it further, 25 to 35 kV, it is not plotted here, what you will see, obviously the intensity will increase, but the position will stay same. Okay, the K alpha position, lambda, the lambda will be same. So, it is very unique of a metal, in this case target metal, it is called characteristic, it is unique, right. And what gives rise to these, right, that is important. Next question is, what gives rise to these maximas, intensity, suddenly the intensity is increasing, right. Basically all of you have studied this in elementary chemistry. So, you have this nucleus, right, surrounded by different cells, K, L, M, N, right. So, what happens, you have these electrons moving at really high speed striking the metal. So, if that electron has enough energy to knock an electron out of this K cell, what will happen? There is a vacancy. Now, the electron from L shell will try to take its place, right. So, this gives rise to K alpha. Suppose there is an electron in M shell, if it tries to take place of the K cell, it calls K beta, right. More likely you will have K alpha because you are closer to the nucleus. So, this is the reason why we get these, right. Also you will see L alpha, because if something can strike, if something can knock out an electron from K shell, obviously it will also remove electron from L cell, M cell, but they will be of much higher wavelengths, right. So, this is the unique thing where we can use this X-rays to probe, because first of all lot of experiments like X-ray diffraction, in diffraction experiments we use monochromatic radiation. Monochromatic means we want only one lambda, right. Here you are getting that unique lambda. Okay. Next slide I will go over, like right now you can see K alpha, K beta, right. You can say okay, you have two wavelengths, but there are ways to filter it out, but at least you know that if you have to get a unique wavelength, you can get it. Okay, that is the characteristic line of that particular target metal. Okay. See, without going much in detail, now the question comes, okay, lot of experiments, we need monochromatic radiation, single wavelength, how do we do it? Now we can use some filters, like filters which will absorb. So in this case you see, we see the nickel filter. So when you apply nickel filter, it will have that absorption band between K alpha and K beta. So basically it will be able to absorb. So you, after applying the filter, you see, you only see K alpha, not K beta, right. So this is one of the ways to filter it out, right. Now you know how to, what gives rise to these characteristic lines, right, and they are very useful because you have now a single wavelength, right. And in this case, pay attention, what is the wavelength? Very small, right. We are talking about few, like in this case maybe 1.4, 1.5 angstrom, right. So these have very small short wavelengths. Typically that is the order of your atomic spacing in crystals. So that is what makes these X-rays useful. Okay. So initially, I mean, diffraction came quite late, right. So but people know that these X-rays have very high energy, they can probe thick pieces of metal, wood. So radiography was initiated without any precise understanding of the radiation used. Okay. You can get a radiograph, you place something on the, before X-rays and you will get a radiograph. It was not until 1912 that the exact nature of X-rays was established. Okay. It took quite a bit of time, although the X-rays were discovered in 1895 by Röntgen, right. This year the phenomenon of X-ray diffraction by crystals was discovered. So this discovery also proved the wave nature of X-rays and provided a new method for investigating the fine structure of materials. Okay. So now we know what are the X-rays, how they are generated, what is so unique about X-rays which we can use to probe the material, crystalline materials. Okay. So now we will now consider the geometry and structure of crystals in order to discover what there is about the crystals in general that enables them to diffract X-rays. So now we know about the X-rays. We are trying to now we know that okay, X-rays can be used to probe crystalline materials. So for that we need to understand what are the crystals, right. So now I will focus on crystals basics, so that then we can connect later on X-rays to X-ray crystals. That is the goal. So crystalline material is a solid with atoms arranged in a repeating or periodic array over large atomic distances. Okay. It has long range order, there is a periodic arrangement, long range. Okay. Repetitive 3D pattern, you notice a repetitive 3D pattern, in all 3 dimensions there is a repetition. And the unit cell is basically a basic repeating unit, that is the cell which gets repeated. And the directions in the crystals are the vectors in 3D space, okay, and the planes are surfaces in 3D space defining layout of atoms. These are just basic terminologies. And obviously the properties of crystal will depend on the spatial atomic arrangement, okay, where are they placed, right. So crystal, a solid composed of atoms, ions or molecules arranged in a pattern periodic in 3 dimensions. Clear? From this picture you can see there is a periodicity, right. And crystal represents the geometry of periodic arrays. The crystal is then represented as a lattice, that is a 3-dimensional array of points, each of which has identical surroundings, right. Here you can see this is the lattice, right, it has identical surroundings, and this is the thing which gets repeated. and 3-dimensional lattice with a primitive unit cell highlighted in bold. So, this one is primitive unit cell. It is called primitive because it has one atom per unit. We will come back to it. One atom is because there are, this is the primitive, right. So, it has 8 atoms, right here, 2, 3, 4, 5, 6, 7, 8, right, and each atom is shared by 8 unit cells. So, you have 8 times 1 by 8 gives you 1. Okay. Okay. Little bit of background. You may already be familiar with this, but just for completion, it is important to review the basics. So, points, lines and planes, right. So, in crystal, what is specific is we are talking about A, B, C, so lengths in 3 dimensions, right, along x, y, z, A, B, C, right. Also, what is important is the angle between these, right. Gamma is angle between A and B, alpha is between B and C, and so beta is between A and C, alpha is between B and C, right. So, these are 6 things we need to know, right, about if you want to figure out which crystal system it belongs to, right. Lines. So, you see here, it is obvious, if you have to represent this, this is 0, 0, 1, right, this is 1, 0, 0 in this direction, right, 0, 1, 0, okay. This is a vector basically, right. Now, the planes, how do we define planes, right, that is important. So, for that we will use the Miller indices, right, that is the system Miller developed to define a plane, okay. So, in this case, suppose we have this plane, right, which cuts A axis here, B axis here, C axis here, right, this is the plane, right, we are talking about this plane. Basically, it cuts A axis at 1 angstrom, this is the 1 angstrom, this is 4 angstrom, okay, this is 3 angstrom, okay, and total length is 4 angstrom, right, this is 4 angstrom, this is 8 angstrom, that is the total length, clear, right. Now, we know the axial lengths, right, 4 angstrom, 8 angstrom, 3 angstrom. Intercept length, this plane is cutting these 3 axes at different points, right. So, intercept with A is 1 angstrom, right, 1, intercept with B is 4 angstrom, right, intercept with C is 3 angstrom, clear. Now, what we do, we calculate the fractional intercepts. So, it will be 1 over 4. 1 by 4, 4 by 8, 3 by 3. So, you get 1 by 4, 1 by 2, 1. Okay. So, the Miller indices will be 4. Now, you have to get rid of these fractions. Okay. Also, you have to invert it. So, fractional is 1 by 4, 1 by 2, 1. Now, you invert it. So, becomes 4 to 1. Why this inversion? You must be wondering why we have to invert. Sometimes what happens, the plane does not cut an axis. So, you may say, okay, the intercept is infinite. So, rather than dealing with infinite, it is better to deal with zeros. How do you get 0 from infinity? You divide, 1 by infinity is 0. That is why, that is how this system was developed. So, basically what are the Miller indices? The reciprocals of the fractional intercepts which the plane makes with the crystallographic axes. Any plane, right, will make some intercepts. So, you have to calculate those intercepts, and then it is a reciprocal of the fractional, that is the key, reciprocals of the fractional intercepts. So, in this case, this plane will be 4 to 1. Okay. So, any plane with this indices HKL, right, will have A over H intercept with A, B over K with B, and C over L with C. Okay? Is it clear? Again, going over Miller indices again, these are the planes, right. So, you have A, B, C, 3 crystallographic axes. So, plane 1, 0, 0, right, is this is the plane, right. It will have intercept of 1 only with axis A, right, because other are. So, how do we get this 1, 0? Suppose this is the plane, right, it is having intercept of 1 with A. Infinity bit is not cutting B, right, it is not even cutting C. It says reciprocal of these intercepts. What is the reciprocal? 1, 0, 0. And the way you represent these planes is in bracket, parentheses. That means that's how you designate a plane. So, similarly now 2, 0, 0 will be somewhere between. Okay. How do you get this 2, 0, 0? Now suppose your intercept is 1 here, in this case your intercept is 1 by 2, right. And again, why intercept with B is infinity, intercept with C is infinity. Now you reciprocate it, you become 2, 0, 0. It's clear. That is how you get this. In this case, now you can work it out. Idea is you have to find the intercepts with 3 crystallographic axes and then get the reciprocal. That is how you define the plane. And when there is a negative sign, then you put 1 bar. So, you see here this plane is represented as 1 bar 1 0. Okay. So, you can practice and see how do you get this Miller indices. On your right, what you see, so again these are the planes, like lines for an example. We are now not focusing on C axis, we are only talking about A and B 2 dimension, right. So, this is your 1 0 line, okay. This is suppose 1 3, okay, 4 1, 4 1 bar. What do you notice? See, these things you can again get it, right. You can calculate how these are again Miller indices, right. You can arrive at these Miller indices. So, observation is the lines of lowest indices have the greatest spacing distance of lattice points. You see 1 0, you have more space. As you go towards higher indices 4 1, your spacing is reducing. Is it clear? See, the difference between 1 and 4 is very obvious, but that is a general. So, if your term, so the lines of the lowest indices, right, lowest is like 1 0, have the greatest spacing density. That tells you about the arrangement of atoms if you are talking about the planes. So, it gives you insight, right. You find out that if you compare 2 different planes, it will tell you, okay, where you have closer spacing for an example.